So this is joint work with Andy Gill at KU, and our motivation for this. So I have this domain-specific language called diagrams, which is for creating vector graphics. It's embedded in Haskell, so you write Haskell programs to describe the images you want, and it can render them. I've just put the URL up there in case people are interested. I'm not going to talk about diagrams today specifically, but the motivation was, okay, we have this nice system for producing images. Can we use it to produce animations as well? But we really wanted to sort of get at the foundation of, what is an animation, and what are the right abstractions for creating animations. So just to say, this is very much a work in progress. This is just a demo. It's still changing a lot. And in fact, the other night I sat down with Nick Wu. I don't know if he's here, but yeah, okay. So and I showed him these slides, and over the course of about 2 hours, he convinced me that most of what I'm about to show you is wrong. But wrong in interesting ways. And I mean, the point is, it's still changing. We're still figuring out what the right abstractions are. And this is really, I hope to get people's feedback about this. So our beginning point, although as you'll see, we ended up in a very different point. But our beginning point, Andy Gill and his student Kevin Matledge had this paper called "Every Animation Should Have a Beginning, a Middle, and an End," and their model was sort of time-varying values. So this is some timeline here, and you can think of the wiggle as the values of some function over time, and it has like an end point, a start point, and an end point. So the model here is like I have a start time paired with a function from time to values of some type A paired with an end time. So okay, if we can take that as our starting model, but then the obvious question is, what operations can we do on these things? It seems like we want to be able to do, very common to have some kind of sequential composition operation to sequence things in time. We're going to have some kind of parallel composition to have things, sort of happen at the same time. Okay, well it's easy to say that, but then what do these operations mean? What are the semantics of these operations? And we're kind of still falling down the rabbit hole of trying to figure out what these operations mean. So through the course of thinking about these, I'll just highlight a few sort of generalizations we had to make and motivate them, and then also tell you why they might be wrong. So one thing we decided is that we wanted to be able to support infinite values. So at the very end, if you're producing an animation, you want to have something finite so that I can produce a movie. Usually those are finite. But it could be useful in describing an animation to have some animations that are infinite. So you say, I have something that loops forever. Because maybe I want to combine it with something else, but I don't know how long that other thing is going to be. And so I don't want to have to say up front, oh, this needs to be 20 time units long, because I don't know how long I'm going to need it. So supporting infinite values, it makes some things tricky. We were also thinking about if you want to sequence two things in time, what happens exactly at the point where they meet? What is the value that you end up with there? So one possible answer is that, well, we have to keep track actually of whether the endpoints are sort of open or closed. Is there a value at the endpoint or is there not? And then you would say you can only compose two things in sequence if one of them has a value at the end and the other one doesn't. Then you don't have problems with things matching up. This makes the types really complicated, and so I'm not sure this is the best way. I was talking with Nick, and we have some other ideas maybe, but maybe just some ways that the programmer can have better control over, if there's a clash, the programmer can say, what should you do? Should you combine the values somehow or throw one of them away? Things like that, rather than tracking in the type system, sort of what's open and closed. And this actually, I think, is one of our most interesting ideas. And this, it's actually implicit, I think, in a lot of other work in this space, that we really want to think about, instead of values that start at some particular time and end at some particular time, is think about if I take one of those and I translate it in time, and then if I can consider any of those translations equivalent. So really what we have are sort of these equivalence classes of things, where you have some time varying value that has a duration, but it doesn't necessarily have a particular location in time. And if you're only dealing with finite values, then you could just say, well, normalize everything so they always start at 0. But if you have these infinite values, that's problematic. You can't just say it always starts at 0 because you don't have a start point. And so how do you deal with that? We're still figuring that out with some ideas. But so right now, we have a Haskell implementation of this. I think, as I said, this is probably we're probably going to throw all this code away and start over, but we'll not start over completely. But, so the types we have. So F indicates whether whether an active value is one of these fixed values that has a specific time, or one of these equivalence classes that's free to move around. We track whether the left and right endpoints can be open or closed or infinite. And then we have a type for time values and a type for what the values are at each point in time. So here's an example of the kinds of types that you end up with for these operations. So here's parallel composition. So it has to take two fixed things because you need to know where they line up with each other. And right, you have to do some funny fiddling with, if you need to keep track of what kind of endpoints you have to take some kind of intersection to figure out what type of endpoints you'll have on the result. And there's actually a lot that I'm sweeping under the rug here, but I don't have time. So, right, and then sequential composition would say, well, you can compose these equivalence class things as long as their endpoints match up in the right way. So that's this compat constraint. Although, as I mentioned, there are other ideas of how to deal with this. So this has been a really interesting journey of, oh, whoops, I forgot to kill that. Of thinking about, trying to think about the semantics in a deep way, but then, of course, we want to encode it. We want to embed it in Haskell. And so maybe there's some, just figuring out the right path through, should I say, maybe the sort of ideal that we have in our heads we can't encode, and so we have to make some compromises. So some issues that come up. Sometimes we really want some dependent types to be able to say the type of this thing depends on when it, how long it is or when it starts. You can't really do that in Haskell. And those types I showed you, there's a lot of things going on, and how do you present that to the programmer in a way that it will be precise, but they will still be able to use it and not just get lost in all the types. Okay, so this is a demo, so I will actually show you some things. So here is a very simple program. So this creates, this rote thing. It says it's an animate. So T2 is a transformation in two-dimensional space. So this is an animated transformation. And it says, okay, create a duration 1. So dir value dir 1 says create something of duration 1, and it should take on the value at each time of the duration since it starts. So it'll go from 0 to 1 over the course of one time unit. And then it says, okay, then turn that into a rotation of that much of a circle. So this represents a rotation that's at time 0 starts as the identity, and then over the course of one time unit, it'll do a complete rotation. Right, then we'd say, okay, create a unit square and apply this rotation to it over time. So then we get an animated diagram. And then we just put it on top of this static canvas and make it take 5 time units. This little star right arrow operator can stretches things in time. So this says make it 5 times longer. Oops. What did I do? Ah. Oops. It's not a diagram, it's an animation. It's not very fast, right? You can't really use this for real-time animation, at least not yet. But face, there we go. You get a square rotating once over the course of 5 seconds. Right, and you can do various things like so maybe I'll make a movie out of, let's say, the same rotating square over 3 seconds, and then maybe run the same thing backwards over the course of 2 seconds. And then we can run this. Takes a while to compile. So there we go. Do various things. How much time do I have left? Okay, great. So let me show you a larger example that I prepared earlier, because I prepared this one earlier as well. So it takes about a minute to compile, so I'm just going to play you the one that I already compiled. So this is sort of a visual proof of the Pythagorean theorem. And this is about, I don't know, it's maybe about 100 lines of Haskell, built on top of this library for animation and diagrams. So we have some like keyframing operator that you can just give it 2 diagrams and it'll smoothly transition between them. Oh, there we go. So, right, Pythagorean theorem is true. Right. So I don't know if there. So here, here's the code. I don't know if there's. I guess that's probably pretty small. There's a lot in here. I could, if people have specific questions about how we make things work, I could answer them. But a lot of this will probably change anyway. So maybe it's not too useful to walk through the code. But so the idea is to make this kind of thing really easy and intuitive for a programmer to build these kinds of animations. So I'm happy to answer questions. Okay, yeah, that's a good question. So the question is, what's the process to go from this, a file like this to a video, and why does it take so long? Right now, so basically when I first started doing this animation stuff, I spent about 5 minutes and I wrote the stupidest possible compiler that I could for animations, and that code is still there. So it just samples the animation over a whole, a sequence of time values, and then generates a bunch of frames, and then uses FFmpeg to put them together. So part of the reason it takes so long is that it's recompiling every frame from scratch. So in the diagrams framework, we actually have quite a lot of sort of structure there, and in theory, it should just be sort of some engineering work to keep track of more information about the animation, so that oh, this part isn't going to change, this part is rotating, so I'm just going to maybe output an SVG and have some JavaScript that does the rotation. Sort of compile the animation into something more direct rather than generating a bunch of frames. So, yeah. Mm-hmm. I'm not sure I understand your question. So what do you mean by things interacting? Ah,
That's usually what animators want
right,
to
right.
control things easily at that point.
Okay, so the question is about, controlling things at the level of sort of, can I animate two things, then have them bounce off of each other, or, I mean, the diagrams framework itself gives you a lot of that kind of information. I don't have a good story for how you sort of extract that information and use it to build an animation, but I think that's a great area for future work.
Can you briefly summarize Nick Wu's criticism?
So yeah, that's a good. So the question is to summarize Nick Wu's criticism about why all this is wrong, or sort of what maybe a better way is. Maybe that's a better way to say it. The thought is to work. So the interesting thing is we started with this model of where things have an absolute time, and then we decided we figured out, oh, for sequential composition, sort of fundamentally it seems like these are acting on these equivalence classes instead, and then. As I'm writing this, I mean, you can see all these types. It says free, free, everything is free, and it seems like you don't really want to work with the things at absolute times. If I say I want a square that's rotating, I don't want to say, oh, it's going from time 4 to time 8. I just want to say it's a square that's rotating, and then I want to have ways to align those with each other, but I don't want to have to talk about absolute time. So the big question is, what does parallel composition mean for these equivalence class things? How do you do the alignment? So you just need a way to do alignment of things rather than they exist at absolute points in time. So, yeah. Yes. Yes, absolutely. There's a connection to the work on tiling that we saw. There's definitely connections to your work on temporal media. We're still kind of figuring out what the relationships are and how those things fit together. Yeah. Yeah. So so the question is, could we just generalize diagrams to 3D and just use that for for alignment? So diagrams already is generic over the vector space, and so actually someone is currently working on adding a bunch of 3D primitives and backend, like OpenGL and Pavre backends and stuff. Yeah, but no, I understand that. Yes, no, I know the question is, can you treat the third dimension as time? So I've thought about this, and I haven't figured out it. It kind of seems like the kind of composition you do in time is similar, but sort of fundamentally different from the composition that you do in space. And I would love to be wrong about that, because this would be really cool if you could sort of generalize over both. And I don't know how to do it right now.
Next question. So in diagrams, you have these wonderful envelopes that help you to assemble things by juxtaposing them.
That's right.
Related to juxtaposing on time.
Yes.
If you extend to some sort of coherent 2D space of 1D time, then maybe it would be really interesting to shape envelopes.
Yeah, you might be right. So an envelope in 1D is just is one of these synchronization periods, right? I think there are interesting things there. I agree, and I don't know what they are, and I would love to understand it better. Yeah. Okay, thanks.